Hi everyone, I'm going to be talking about the metabolism in this section. Okay, so the purpose, provide basic information on energy metabolism and bioenergetics that will be useful in helping personal trainers or anyone in the medical field that helps people plan safe and effective exercise programs for the clients. Objectives, okay, we're going to describe the primary method of how the body produces energy, differentiate between aerobic and anaerobic metabolisms. I'm going to go a little bit on the pathways. I'm not going to get really in depth on the Krebs cycle. The Krebs cycle. It's because that may be a little too much for this course. Maybe I might add in a little video for you to watch on there. The Krebs cycle is important. I'm very rusty at it, as I have to stay on top of it. It is a little complicated, by all means. It's really, really good to know, especially if you want to do anything more in the future of exercise science, health-related matters. Really, really important to know that. But I'm not going to really go really in depth on it in this course, so you know. We're going to talk a little bit about different energy states, requirements for energy, and so forth. All right, so what is bioenergetics? So bioenergetics is the study of how energy is transformed through various biomechanical reactions. So metabolism, okay, we talk about metabolism, refers to the chemical reactions that occur for the body to maintain itself. Now, exercise metabolism is the same thing, but how that body kind of adapts during exercise and activity. We talked a little bit about the nutrients, so the macronutrients, okay, the fats, carbs, and proteins. Okay, so carbs provide the body with probably the most efficient source of fuel. The storage form of carbohydrates is called glycogen. Okay. Your body likes carbs the best. It uses probably the easiest, and that may be why everyone loves carbs. Everyone likes the pastas and pizzas and so forth. Okay, fat is the next one. Okay, chemical or substrate form in which most fat exists in foods, as well as the body, is called triglycerides. Okay, so a lot of times fat is often termed triglycerides, just so you know that. A lot of people view fat as really a negative thing in terms of like food. You should avoid, obviously, like excessive fat, but you shouldn't like cut it up completely because you still need a good amount of it. The third one's called proteins. Okay, also referred to as amino acids, just however you want to refer to it as. Protein is rarely used for energy, just because usually your body relies on those protein stores as muscle to do some kind of activity. If your body ever ends up using protein, it's usually not a good thing. It's usually out of fats and proteins, out of fats and carbs, so it has to resort to the proteins, which isn't good for your body. It actually takes it just pretty much out of your muscles. Exactly. But that's a really, really diminished state of malnutrition or just starvation at that point, or if you have to resort to the protein usage. It does use your proteins a little bit, but not to this extent of like carbs and fats. Fats provide the most energy just because of the high energy content that's stored within fats. And so our body likes to store those in case we need them. ATP, so adenosine triphosphate, okay, is the primary source of energy in all of everything. It's the best one. It's best for our immediate energy. That energy is stored in the chemical bonds, and that is an adenosine plus 3 phosphate molecules. I'm not going to get really in depth on the chemistry on that. So in the chemical bond, that ATP is broken, the energy is released. It usually results in now a phosphate and then a diphosphate, or ADP. ADP is required, or sorry, ATP is required to perform mechanical work, pretty much all mechanical work. So the three systems we'll talk about is the ATP, or the phosphocreatine system or cycle, that provides energy for short-term duration, high-intensity work. ATP usually is diminished or exhausted usually within about 10 seconds. So this is that first sprint, the first initial sprint, or whatever that is, that first initial quick movement. That is just all that little bit of reserve ATP that you have. The next one is going to be glycolysis. That provides energy through the breakdown of glucose to create ATP for moderate intensity, moderate duration work. So about 30 to 60 seconds, give or take. And the last one is going to be your oxidative system. Okay, so this is the most complex. It has three main systems within itself. A process which uses the substrates and with the aid of oxygen to generate the ATP. Okay. So they're all, usually when you're doing activity, you're going to use all three systems at once. The first one's going to be primarily your ATP system, or phosphocreatine system. That's going to give you the most energy. And the next one is going to be going to be the glycolysis. Okay. Most of the time, that's some kind of anaerobic respiration or anaerobic metabolism, however you want to refer to it as, to where the body's not really using oxygen for that process to produce that energy. And so it's going to last maybe up until the first minute or so. And then after that, your performance is usually going to decrease, and you rely directly on your oxidative system or your aerobic system. So that one's going to use oxygen to produce most of that energy. And so you're not going to have like a high energy content during that. Let's be moderate, but you're going to be able to go for a longer period of time. So a little bit more about the oxidative system. So the three kind of systems or aerobic systems could be one, the aerobic glycolysis, then the Krebs cycle, and also to be the electron transport chain. So fat is also to be metabolized aerobically. The first step in the oxidation of fat is the process referred to as beta oxidation, just so you know. So a lot of ATP is produced through these cycles, especially the Krebs cycle. Okay, a little bit more. So glycolysis, okay, occurs in the systole of the cell. Okay, so just floating around there. Excuse my dogs. Breaks down glucose into two pyruvic acid molecules, and this produces only 2 ATP per glucose molecule. Just so you know. Okay. Next one is the anaerobic respiration. Okay, so the breakdown of glucose in the absence of oxygen, obviously. Hence the anaerobic. Produces 2 molecules of lactic acid and 2 molecules of ATP. Okay, there's 2 kind of phases of this. The first one's going to be what we just mentioned previously, the glycolysis. So the anaerobic respiration produces 2 pyruvic acid molecules and 2 NADH. The next phase is going to be the lactic acid formation. Okay, the conversion of pyruvic acid the conversion of pyruvic acid into lactic acid. Okay, so this is where you get your lactic acid really accumulations right here. All right. Next would be the aerobic respiration we talk about. So breakdown of glucose with oxygen to produce carbon dioxide, water, and then aerobic respiration can produce 38 ATP molecules total per cycle of everything. So the acetyl-CoA formation is going to be the pyruvic acid gets broken down into carbon dioxide. The acetyl-CoA, which you can think that is like a subparticle of the fats and the triglycerides, it's produced as well, and that kind of goes more into the Krebs cycle, which we'll talk about here in a minute. And during the acetyl-CoA formation, it produces 2 NADH and 6 ATP. The next portion is going to be the Krebs cycle. also called the citric acid cycle, but everyone knows it as the Krebs cycle for the most part. So just immediately 2 ATP is produced. Then the cycle goes on 6 NADH, which in turn produces an additional 18 ATP. And the last will be 2 FADH2, which ends up producing 4 more ATP. So just the Krebs cycle alone produces 24 ATP per cycle. And that, along with the acetyl-CoA and then a little bit of the glycolysis, produces up to 38 ATP. So this right here is slightly off topic, but I want to include it in here. It's a little bit of kind of breakdown, if you will, on amino acids. Okay, so this is the protein. Once that gets absorbed, protein gets taken out of there, and the non-essential amino acids kind of kick in. And this kind of can kick out some ammonia, energy, some ketones, and acetyl-CoA, and so forth. And it kind of goes and gets absorbed by your muscle. The triglycerides, or your fat, gets absorbed and processed and gets broken down into the fatty acids, the free fatty acids, and some more glucose. Those into your triglycerides get stored as adipose tissue, or fat, as we know it as. And also would be your carbs. Okay, so carbs is broken down to glucose, glycerol, glycogen. Okay, and gets stored in pretty much most of these processes as gets converted to energy, stored in muscle tissues, ATP, and it also helps with the storage of some fats, and also gets stored in your muscles. So all these get utilized pretty broadly, especially the carbs or the glucose, because it helps with all these things. I just want to kind of include this in here so you guys can get a little bit of understanding on how what we eat gets kind of broken down and absorbed. And then energy during exercise. The intensity and duration of the exercise are inversely related. So amount of energy available from the stored ATP or the phosphorus-creatine cycle is pretty small. Okay, that's the first few seconds or so, because you have just available ATP ready, and that's going to be that first sprint, and then you kind of die off a little shortly afterwards. The amount of energy from stored carbs has a higher capacity, but still limited. I mean, the carbs are stored, and then it has to be broken down to be used. Okay. The amount of fuel from exercise from fat is essentially unlimited, just because you get about 9 kilocalories per, I think, gram of fat, which is a lot higher than the carbs and protein. The cost of exercise varies, obviously, depending on the condition. For example, when we're lying down in bed, we're not really using or burning a lot of calories. We're still burning calories throughout the day, even when we're not doing anything, just to maintain our current metabolism. Your body does prefer that oxidative state. And then after you do some kind of activity, for example, that post-exercise oxygen consumption, or the EPOC, this just helps, even though you're done with the activity, for the first few minutes afterwards, you're breathe heavy. That way your body can start to build up that stored ATP. And then during intermittent work, glycolysis provides energy for work. Oxidative system provides a good amount of recovery. Okay. So the glycolysis, that's going to be our mid-range system. So most of the time, if we're not doing crazy long distance, long duration stuff, it's going to be primarily our glycolysis. And fuel contribution during exercise. So for this one, to get your respiratory quotient, it kind of measures your CO2 and your oxygen consumption, and it varies. And it's through this metabolic analyzer, which looks identical to a breathalyzer. I can't speak. Breathalyzer for alcohol-wise. And so if it picks up a 1.0, it indicates that you're using primarily carbs for your fuel. If it's 0.7, it means you're using 100% of fat. But usually you're going to be somewhere in between, using some kind of combination of the two, depending on what it is. So quick summary, okay, on the bioenergetics. Um, the metabolism, okay, obviously refers to a lot of different things. A lot of chemical reactions that goes on. Proteins, carbs, and fats, these are your macronutrients. ATP is the chemical formation of energy and used in all of the three pathways. And then the RQ, uh, respiratory quotient, used to determine what percentage of fats and or carbs that you're using. You can buy those. They're, I think, about $100, give or take. So you can have them if you really, really want to know. Usually what's going to be is you're doing you can just kind of like eyeball it. If you're doing, if you're like lifting weights, for example, you can kind of get a general idea of what system you're using in versus if you're running 5 to 10 miles, give or take.